Okay, good evening. I was discussing for few classes, I think last two classes uh, regarding the isentropic flow. And the last class I started discussing on the isentropic flow through a converging nozzle. First thing that we have to remember or understand that we are actually going step by step. So the discussion was regarding the development of velocity. Say this was the topic that I discussed in the last class. Isentropic flow through nozzles. That is a convergent nozzle. Okay, convergent in the convergent nozzle, we have discussed that the maximum velocity at the exit will be the sonic velocity. So at the exit, the maximum velocity will be sonic velocity. Yes. Can you please accept our visit? Please waiting in the lobby. Okay, okay. Yes, yes. Yes, yes. Okay, you can remind because I am looking at the screen and I have muted the mobile, so I may not be able to see. So okay, one you can remind me surely. Okay, okay. Okay. So you try to understand the step-by-step development of our discussion. Okay, so what we did try to I am recapitulating the whole discussion that I had done for the compressible flow. First, I had discussed the definition of the compressible flow and what is the criteria for calling the flow as a compressible flow, and mentioned that for the compressible flow, the velocity is a criteria. That means the kinetic energy is a substantial quantity which cannot be neglected. In some other applications, the kinetic energy terms we call it that it is a negligible one, and therefore the other terms like enthalpy, internal energy, etc. These things dominate. But for compressible flow, the kinetic energy is a non-negligible quantity, and that is a key quantity which actually play the role, which actually plays the role in the compressible flow. Okay. And in the compressible flow, the velocity is actually comparable to the velocity of sound in the medium. Medium means, for example, the flow is with some medium like air, then then the velocity of sound in that particular medium. So I discussed that thing, and then I discussed about the stagnation properties, which is a quantity which actually plays role in the calculation of compressible flow. So regarding that stagnation properties, we have defined and then assigned a notation as a P0, T0, rho 0, H0, etc. And then we have determined other variable properties like temperature, enthalpy, pressure, density, etc. in terms of those stagnation properties. And then we kept on calculating many things, and then we kept on adding the assumptions uh, during those calculations, like for example for the first calculation like enthalpy, that is stagnation enthalpy and static enthalpy relation. In that case, uh, we had assumed that the flow is adiabatic and there is no work done and there is negligible change in potential energy. With that, we calculated the stagnation enthalpy and static enthalpy relation. And then we also calculated for ideal gas what is the relation for stagnation temperature and the static temperature. Then what we did, we further extended the assumption as isentropic. The flow we assume to be isentropic instead of adiabatic. So for that isentropic flow, we calculated what is the relation between the isentropic, the stagnation pressure and the static pressure. And for the ideal gas, obviously. So we assume the isentropic relation for the ideal gas and then calculated those relation. Then what we did is we assumed a flow in one dimension and then calculated the those properties related to the property called the Mach number. Here, we have to understand that Mach number was defined as a property which is basically ratio of the flow velocity to the velocity of sound at the same temperature of the flow in that medium. So with that Mach number, we have, in terms of Mach number, we have calculated the ratios. Okay. So after that, what we did, we have shown that there are these are the stagnation to static temperature ratio in terms of Mach number that is done. Now those things actually was done for a sonic velocity. That means for the convergent nozzle only. And also we have derived the quantities for different ducts. We have done the calculation for the converging duct. That means we have analyzed from the differential equations, we have analyzed what will happen for converging duct, what will happen for diverging duct. All these calculations and analysis that we have done are recorded and uploaded in the uh, channel, so you can follow that. All these five lectures, I think these are already done, and I have done it a little slowly so that you can follow properly. I have not made very quick lectures, keeping in mind that it is better to go slow than to means very fast, because it will be easier and convenient for you to follow. So that's the reason. The videos are about say more than 1 hour, maybe say 1 hour 30 minutes like that. But I think you will be able to follow. Okay. The size of the length of the video was that was not the target or criteria in my mind that I should be reducing the time, because my target was to make the student familiar with a slow pace, but it should grow in their mind properly. So that was the reason. Okay, now we have what we have done is after getting these uh, differential equations, we have analyzed for different ducts like converging, diverging, etc., and also for that means in terms of area that is converging or diverging, and in terms of Mach number, whether it is supersonic and subsonic, what will happen for subsonic flow, what will happen for supersonic flow, that we have discussed. Okay. Next, we have basically further went on calculating this from the differential equation. We have basically constructed the integrated form of the differential equation and solved those. And we have solved for one-dimensional isentropic flow for a nozzle. And before that, we have also got the thermodynamic relations. That means how the pressure, velocity, Mach number, temperature, density, etc. will vary for different situations. Like you see that it's a Mach number less than one, that means subsonic. Mach number less than one, subsonic. So these two top cases are for subsonic flow, and how the pressure, velocity, Mach number, temperature, rho, density, etc. will vary for a subsonic nozzle. The subsonic means Mach number less than one. Nozzle means the velocity increases, so it's a nozzle. Similarly, subsonic diffuser, Mach number less than one, and velocity decreases. So that is a diffuser. Velocity decreases means diffuser. Velocity increases means nozzle. And this is a supersonic nozzle, so Mach number greater than 1. Here also Mach number greater than 1. And velocity increases, so it's a nozzle. Velocity decreases, pressure increases, it's a diffuser. And also I had mentioned it clearly, showing by mathematical form that pressure in all these situations, follow this diagram very clearly. That should be clearly understood and kept in mind forever. You see that pressure decreases, velocity increases. That means for all situations, you will see that whatever will happen with pressure, with velocity, the opposite thing will happen always. So if pressure decreases, velocity will increase in all situations, irrespective of whether it is a converging or diverging, or whether it is supersonic or subsonic. That should be kept in mind and that should be understood properly, that relation between pressure and velocity is independent of whether it is Mach number one less than one or greater than one, or whether area is increasing or decreasing. Pressure and velocity will always vary in the opposite manner. Okay. Another thing is that uh, pressure, temperature, and density will always vary in the same manner. Okay. Pressure, temperature, and density will always vary in the same manner. So see the first diagram, pressure decreases, temperature decreases, rho decreases. You see this one, pressure increases, temperature increases, density increases. You see the third one, pressure decreases, temperature decreases, rho decreases. You see the fourth one, pressure increases, temperature increases, density increases. So it will be easy for you to follow that pressure, temperature, and density will be always varying in the equal or likely manner. However, pressure and velocity will be always varying in the opposite manner, whatever be the situation. Okay. Now, if the velocity increases, then Mach number increases. If the velocity decreases, then Mach number decreases. If the velocity increases, then Mach number increases. If the velocity decreases, then Mach number decreases. So velocity and Mach number, they will follow the same trend, means in terms of increment or decrement. Okay, is it clear? That picture should be kept in mind forever. Okay, there should not be any confusion. So pressure velocity variation. They are directly proportional. Yes. So they are directly. Directly, exactly. So pressure, temperature, and density, they are directly proportional. So their variation will be in the same direction. Pressure increases, temperature increases. If the pressure increases, then temperature and density will increase. Okay, but if pressure increases, velocity will decrease and Mach number will decrease. Okay, so if you can understand one diagram, then all the four are clear, right? Okay. Yes, sir. That should be clear. Okay. So that is very important diagram in compressible flow. There should not be any confusion because there are so many quantities. People may get easily confused that how to follow what should be the trend. So that is this. That means the pressure and velocity will be always varying oppositely, and the thermodynamic properties like pressure, temperature, and density will be always varying in the same manner. And velocity and Mach number, since they are directly connected, so velocity and Mach number, they will be always following the same variation. Okay. Okay. Next, we have determined the property relations in terms of Mach number for ideal gas for isentropic flow. So K is the isentropic index. Here it is related in terms of Mach number. This is the ratio of the stagnation to the static property, and here it is the ratio of the when the critical Mach number is 1, that flow is called the there. It is a sonic condition reached, and that all those quantities are termed as critical quantities. Like T star is a critical temperature, P star is a critical pressure. That means when there will be a flow uh, and the flow reaches the sonic condition at the throat, we had seen that the flow will reach at the sonic condition. The flow will reach at the sonic condition only at the throat, only at the throat. It will not reach anywhere else. Say, for example, if there is a flow, the sonic condition will not reach somewhere here. Sonic condition always will reach at the throat. And corresponding to Mach number 1, that quantities are called the critical quantities like T star, P star, rho star. Okay. And another thing that I told is that it is not always true that at the throat there will be always sonic condition. But the reverse is true, that if there is sonic condition, that will always be at the throat. Okay. So that I discussed. So critical properties and critical property ratios in terms of isentropic coefficient. So this is a fixed thing for a particular gas. That means when we consider the constant value of the isentropic index, so this is a constant quantity for a particular material. Okay. So we have basically tabulated these ratios for uh, some uh, that is standard materials like steam, superheated steam, combustion product, air, monatomic gas, etc. Okay. Okay. So now what I will do is, you see that what was our target? To discuss how to get maximum velocity, right? So that was our target. Now we had seen that in the last class that for an isentropic flow through nozzles, that is this kind of nozzle, where we have a convergent nozzle basically, and starting from the stagnation properties, the maximum velocity that we can reach at the throat is the sonic velocity. And if we try to reduce the pressure for increasing the velocity further, there will not be any increase in the velocity, and the pressure at the exit will be the pressure at the exit will be the critical pressure, that is P star, and the back pressure may be further reduced, but the critical pressure, the pressure at the exit of the nozzle will remain as the critical pressure, and the pressure variation in the nozzle, that is throughout the nozzle path or throughout the length of the nozzle, that will remain as it is. So that is the condition we call that. After this condition is reached, the flow is called choked flow. because after that there will not be any change and the flow condition does not change. We cannot change any further mass flow rate. If we try to increase the length of the nozzle and the exit of the nozzle is further reduced in area, then the opposite thing will happen, because the velocity will remain the same at the exit, but the mass flow rate will reduce because of the lower area. Okay, so that part we have discussed, and also we have calculated the maximum mass flow rate. So this is the maximum, this is the mass flow rate equation. And that was actually mass flow rate was actually in terms of the pressure, sorry, density, velocity, and area. So we have replaced those things in terms of the stagnation properties, and we have calculated the or represented the mass flow rate. Now, what we have done is we have calculated the condition of maximum mass flow rate, and we have seen that the maximum mass flow rate is reached at the condition when Mach number is 1. So that is the sonic condition at the exit. So when the exit velocity is same as the velocity of sound, the mass flow rate becomes maximum for a convergent nozzle. This is the convergent nozzle. Okay. So for this, what was our basically observation? That the sonic condition is the maximum condition at the exit. Beyond sonic condition, that means with this type of nozzle, we can never get supersonic flow at the exit. That was the key observation or key outcome from the calculation. So with this type of nozzle, we can never get a supersonic flow. Okay, so area, if the area is reducing, we have seen that under subsonic flow the velocity will increase, but it will increase only up to the sonic velocity. Beyond sonic velocity means it cannot cross the sonic velocity with this reducing area. So we had seen that if we want to increase the velocity, then in the supersonic zone we have to actually increase the area. Now initially the area was decreasing and the velocity was increasing, but now the area must be increased to increase the velocity. You see this one, you see this one. So this is the nozzle, the first one. So here Mach number less than 1, so starts from here, and at the end the maximum velocity with the subsonic flow can be only sonic velocity at the exit. So with a subsonic inlet, the maximum velocity at the exit will be sonic condition, that is Mach number is equal to 1. But beyond Mach number 1 it cannot go. So what we have to do is we have to basically go for this one, this third diagram, you see, because with that we can go for supersonic condition at the exit. So that is the basically target. Okay. Okay, is it clear? Yes. Okay. So that should be basically clear. Now what we will do is we will go for supersonic nozzle, or basically what was that nozzle type? Convergent divergent nozzle we will go for. Okay. So basically what we will do, we will combine this one. So starting is convergent, and then we will basically kind of join this with this one here, and therefore it will become a convergent divergent nozzle. In the convergent part, starting from the subsonic velocity, the velocity will reach up to sonic velocity, and in the divergent part, starting from the sonic, it will further increase the velocity to supersonic. So in the convergent part, it will be basically reaching up to sonic, and in the divergent part, it will make it or take it beyond the sonic and it will make it supersonic. Okay. Okay. Next, what we will do is, we will calculate. So this part we have seen. This up to this we had seen in the last class. I will discuss how to get that from this. That means we assume that Mach number is equal to 1. That is the condition for maximum mass flow rate. And we had just put Mach number is equal to 1 here and got this m dot x. In a separate class or in a separate lecture, I will give the calculation. So I will attach that lecture with the earlier class and you will get it. This is simply one differentiation and just some rearrangement, and it will be easily coming that for Mach number is equal to 1, we will get it. Okay. So here basically, so this is the condition for getting. So this is the mass flow rate. Now the condition for maximum mass flow rate will be dm dot dma is equal to 0. And from that, we will get this ma is equal to 1. Okay. So that can be easily shown. I will show it. So next. Next, what I will do is, before going for the convergent divergent nozzle, I will just show another calculation where basically, so we have already calculated m dot x. What is that m dot x? This one. This is a m dot max. This one, m dot max. Now, what is A star? A star is basically the area at the throat. And all other quantities that you see, that simply gamma r T0 P0. So this is the maximum mass flow rate for a given area at the throat. So throat means what? Can you say? Can you tell what is the throat? Here?
Sir,
Yes?
at the end area.
Exactly. Exactly. Throat here, it is basically, it is a convergent nozzle. So throat means the exit. So this is the exit area. Exactly. You see that. This is the convergent nozzle and throat means it is the exit. So that is the area at the exit. Okay, so this is the area at the exit. Very good. Next. M dot max we have already got. Next, so what we will show is, max we have got one this 13. Okay. Now what we will basically do is, you see that this relation is the m dot. Uh, m dot is the general relation, and m dot max is the maximum mass flow rate. Now, if we see that, if we basically, that means this is the m dot and maximum velocity is this one. What is that? Maximum velocity. This one. So let us. Okay. Now what we want to do is basically a relation for the variation of the flow area through the nozzle. So for a variation of the flow area, now we want to calculate a relation of variation of the flow area. That means how the flow area varies. So basically, we now want to design that area. Try to understand that. So so far whatever we have done is calculated the maximum velocity. Okay, calculated the maximum velocity. Uh, we have also calculated a general relation or general expression for velocity, general expression for mass flow rate. This is the general expression for mass flow rate, and this is the expression for maximum mass flow rate at the exit. That means A star is what? A star is the area at the exit, and A is what? A is the area at any point. Okay. Now, therefore, we have got a condition that a maximum mass flow rate will be this one when the Mach number at the exit is 1. And here, what is the condition? The condition is that this is a general relation. Here it is not told that Mach number at the exit will be 1. So, for this relation, if the Mach number at the exit becomes 1, then we get this relation. Okay. Now, what we can do is, so even if the Mach number at the exit becomes 1, this is a valid relation. That means even if the Mach number at the exit becomes 1, this, the first one is a valid relation. So elsewhere, that means other than exit, the mass flow rate, which is basically maximum mass flow rate, the relation of mass flow rate elsewhere will be this one. Can you follow? Try to understand that. This is the relation of mass flow rate that we have got from the basic relation, that is simply rho AV. From that we have got it. Now we have determined the condition for maximum mass flow rate as this one, and we have got a relation that is achieved when the Mach number at the exit is equal to 1. That means this is a general relation. In this case, it is not ensured that at the exit the Mach number will be 1. But if we want to get a maximum mass flow rate, that that leads to the condition that at the exit the Mach number will be 1. Now mass flow rate is same everywhere, because mass flow rate is a conserved property. So that means for this condition, when the exit Mach number is 1, mass flow rate is maximum, but that mass flow rate is everywhere same, isn't it? The same mass flow rate, even if it is maximum. So maximum mass flow rate is not at the exit only, that is everywhere same. So this relation is at the exit because the A star gives you A star is the area of the exit. But you see that the what is the mass flow rate here? When the mass flow rate is maximum here, what is the mass flow rate here?
Same, sir, same.
Same mass flow rate, exactly. Now, what will be the expression for that mass flow rate? This one?
M max.
Eta. Now, not that. For that, the mass flow, the relation of mass flow rate will be this one, because in that case here you see here the Mach number may not be 1. So if I write the Mach number is equal to 1 here, that will be a mistake. You see that anywhere else the Mach number is not 1. Are you getting my point? So here that means say here if I try to write say this one, this point, let me take a different color. Yes, say this one here at this zone, even if the mass flow rate is maximum, for that condition what is the MA here? 1. But here it is not 1, MA is not 1, but the mass flow rate is same everywhere. Here the mass flow rate is same as here, as that of here. So mass flow rate are same because mass flow rate is a conserved property. So it is same here and here, equal here and here. But Mach number is maximum here, Mach number is 1 here, but Mach number is not 1 here. So something else, Mach number. So that mass flow rate, it's same as maximum mass flow rate, but the expression for mass flow rate somewhere else is this one, and for the throat it is this one. Am I right?
Yes, sir.
Okay, good. Is it clear to all?
Yes.
Huh?
হ্যাঁ স্যার।
ওকে, বাকিটা আছে তো নাকি?
হ্যাঁ স্যার আছে।
Okay. Okay. It's very interesting. Next, therefore. So if therefore, now our target, try to understand the target. Our target is to, you see, that we have determined the mass flow rate here in terms of A star. Okay, so A star is one assigned quantity. That is, A star means the area at the exit of the nozzle or the at the throat of the nozzle, A star. Now here you see that it is in terms of A, right? So what is that area? This one. This is the area. Now what we want to do is we want to get a relation between A and A star, so that we can design it, so that we can design the nozzle. So it will be a relation between A and A star that will give us a continuous variation. That means how A is varying in terms of A star. So say for example, it will be something here, it will be something here. So A and A star relation we will get in terms of what? Mach number. Okay. All other properties are at the inlet. You see, all other properties are at the inlet. So we will get a relation if we equate this one and this one, because they are equal for the condition mass flow rate are equal at all sections. So if I equate this with this, so m dot will be equal to m dot max, and in that case we will get a relation between A and A star in terms of Mach number. So Mach number at different points will be different, and the area at different points will be different. So area we will get in terms of A star and Mach number. So for this situation, the area variation can be calculated as the Mach number at different location. That means the area at this location and Mach number at this location. So they can be uh, expressed. They can be linked, right? Okay. Okay. Let me show. Now, therefore, if we just equate these two, that means this one and this one, just m dot max is equal to m dot, then we can write, let us see. So m dot is equal to m dot max. Therefore, we can write that, let us copy that. M dot is equal to this one, m dot max is equal to this one. So m dot max is equal to this one. Therefore, if we just equate them, then we will get this is equal to this. This is equal to this. Okay. So that implies, therefore, so m dot is equal to m dot max. We want to express the variable area with location, you can say. And you say Mach number. In terms of A star, that is the area at the throat. Area at the throat. That means we want to design the convergent nozzle. Okay, that is the target. We want to design the convergent nozzle. So this is for maximum. That means what we are actually designing? Designing the nozzle. Designing the nozzle for maximum velocity, isn't it? Maximum mass flow rate.
Yes, sir.
That means we have taken some value of A star. That mass flow rate maximum means what? If I increase A star, definitely the mass flow rate will further increase, isn't it? Isn't it? So if I increase the area, then mass flow rate will definitely increase. Say for example, if I make the area twice of A star, then mass flow rate will of course increase by 2 times. So our target is that I have taken for some mass flow rate, say for example, some target I have assumed. So this is the target mass flow rate, and accordingly I have calculated what should be the area. Okay, so for that area, what should be the area at other location? So that is our target. Okay, so I have taken some value of A star, and then we are calculating what will be the value of A at other locations. Okay.
Yes, sir.
So designing the nozzle for maximum mass flow rate with assumed A star. Okay, so now we will relate A in terms of A star. So that is basically A by A star we will write in terms of this one. So A by A star will be equal to this some quantities will cancel out, like this quantity will cancel out here. P0 will cancel, and Mach number, all this thing will be there. So it will be, so it is 2 by gamma plus 1 whole to the power gamma plus 1 by 2 gamma minus 1. And here also you see that these indices are basically same. These indices are basically same. this one and this one, isn't it?
Yes, sir.
These indices are same, so they can be combined under a single bracket. So this can be cross multiplied and they can be uh, taken within a single bracket. Yes, right. And it will be simply Mach number here. Mach number will go in the denominator on the right hand side. So it will be basically 1 by Mach number one by Mach number and then everything within the bracket. So it is 2 by gamma plus 1 and then it is 1 plus gamma minus 1 by 2 Mach number square. Okay, whole to the power gamma by, I'm sorry, gamma plus 1 by 2 gamma minus 1. This one, right? So that is our relation for variation of area with Mach number. This is the designed area variation. Okay. So tables are there which gives the values of A by A star as a function of Mach number. Okay. So as a function of Mach number for some gas, because the gamma value depends on different gases. So for example, for air, some tables are there which gives the value of A by A star. There is a table. There are basically tables which gives the value of A by A star as a function of Mach number for some gases like air. As Mach number changes, that will change. Okay. Now, we will also define another quantity called Ma star. What is that? Let us see. We define a quantity Ma star is equal to, now we know the expression of Mach number, that is simply the velocity of flow to the or the ratio of the velocity of flow to the velocity of sound. Okay, now Ma star is defined as velocity of flow divided by the velocity of sound at the throat. So this is C star. Okay. So M star is defined as the ratio of the local velocity to the speed of sound at the throat. Local flow velocity, you can say. Okay. So if we try to write Mach number star M star is equal to V by C star, if I write as V by C multiplied by C by C star. So they are basically same. Now what is V by C? We know it is Mach number. So basically what we want to do is we want to express M star in terms of MA. And this is basically C by C star. And what is C? C in terms of the ideal gas, for the ideal gas, it is gamma RT. Now remember one thing, try to understand one thing, that this sonic speed depends on what? You see, during the flow, the temperature is changing, isn't it? The temperature, the temperature everywhere are different. The temperature everywhere are different. So the sonic speed will also change along the flow path. That means sound, the speed of sound will also change along the flow path because speed of sound depends on temperature. Therefore, as the temperature is changing, the sonic speed will also change at different locations. That means C means what? C means the velocity of sound at the local temperature. At some point, say for example, if I take here, so velocity of sound at the temperature here, and C star is the velocity of sound at the throat. So condition of throat. Okay, is it clear?
Yes, sir.
Okay. So therefore, if C is equal to under root gamma RT, then what will be C star? Can you tell?
No, sir.
You see that the velocity of sound is what? Under root gamma RT, isn't it? In terms of temperature. So it is gamma RT. And so the temperature here is T, so it is under root gamma RT. What is the velocity here? What is the temperature here at the exit?
Sir, rises.
Yes.
Sir, temperature rises.
Temperature rises, but means what is that? Is the temperature rising?
Yes, sir.
No, you are
No, sir. No, sir.
mistaking.
Pressure is decreasing and temperature is also decreasing.
Exactly. Because velocity is increasing, so pressure will fall and temperature will also fall. Okay. So
Yes, sir.
what is the condition here at the throat for maximum mass flow rate? What is the condition
Mass
here?
flow.
At at the exit, what is the condition?
Sir, mass flow rate will be equal, sir, and A star will be greater than.
Mass flow rate will be equal, obviously. Now my question is, for the maximum mass flow rate, what is the condition here? When the Mach number is equal to 1
Yes, sir.
at
Yes,
the
sir.
throat, what is the condition? You see, what is the condition? Can you see?
Yes, sir. T
Mach number
star
is
by
equal to
T.
1. Mach number is equal to 1, then T becomes what?
So T star.
Exactly. So, when the Mach number is 1 at the exit, that means for the maximum mass flow rate, what is the temperature here?
T star.
Exactly. So, that is critical temperature. Okay.
Yes, sir.
So, what will be the sonic speed?
Next, it's the maximum.
No, sonic speed. C star. What is C star? What will be this? C star. Temperature, you know?
Yes, sir. T star.
So, what will be the sonic speed?
Sir, root over gamma r T star.
Exactly. Fine. Thank you. So, it will be under root gamma r T star. Is it clear to you?
Yes, sir.
Exactly. Because we know temperature, so we can directly relate in terms of temperature. Because C depends on the material, that is gamma R, and the temperature. So gamma R are same for this material, and their temperature is changing, so that is T star. Okay. So therefore, we can write this as MA simply T by T star. Isn't it? So basically, MA star we can write MA star is equal to MA multiplied by T by T star. Okay. So let us number these equations so that it will be easy for us to follow. So 14, 13, equation 13, m dot max. This is the equation 15. This is equation 15. So this is equation 13. This is equation 15. And this is equation 16. We have defined this. So this is equation 17. Okay. This is the equation 18. Okay. Next. Therefore, you see that here we have got MA star in terms of MA. MA is the local Mach number, and the temperature is T, and MA star is the MA star is the condition. MA star is the Mach number defined in terms of local velocity to the velocity of sound at the throat. Okay. Now, if we want to here you see that how to get it, because we know the relation between T and T star. If we want to get the relation between T and T star, you see that earlier we have got relation between the temperatures. What temperatures we have got? The relation between the T star and T0. We have got a relation, and also we have got a relation between T and T0. So from this we can get or eliminate this T star and T. Isn't it? So what was the relation? Let us just try to see. T0 by T relation. One is T0 by T, another is T0 by T star. One relation was this one. One is this one, T0 by T star. Another is T0 by T, this one. Okay. So let us just rewrite. This is equation 16. Another is this one, equation 9. So you see that if I divide this by this, what will I get? So basically what I am trying to show you that here it is T by T star relation. In any of our, in none of our earlier relations, we have got T by T star. So, but we have got relation in terms of T0 and T and T0 and T star. So if I just divide these, then I will get a relation of T and T star. So that is I'm just going to do. So if I just divide that, so what will I get is T by T star I want to get. So what is that? T by T star. T by T star. So gamma plus 1 by 2 multiplied by 1 by 1 plus gamma minus 1 by 2 ma square. Okay. So T by T star is equal to gamma plus 1. Here it is, if I multiply 2, so it will be 2 plus gamma minus 1 ma square. So under root of this is equal to under root of this. So what is the relation between ma star and ma? Then I can write from equation 18 and say, let us give it a number. After 18, it is say 19. Therefore, from equation 18 and 19, we get ma star is equal to ma multiplied by T by T star, that is equal to gamma plus 1 divided by 2 plus gamma minus 1 ma square. Okay. So this is equation 20. Okay. Now here you see that in the tables, the A by A star ratio is given in terms of Mach number for different values of Mach number. As the Mach number changes, the values of A by A star is tabulated. Also, the values of MA star is tabulated. So, as we know that you see that Mach number has a particular relation between Mach number and Mach number star, MS star. So we can give a particular chart where at different area, at different locations, what is Mach number, what is MS star. MA means local velocity divided by local sonic velocity, or MS star means local velocity divided by the sonic velocity at the throat. Okay, that is the difference. Okay. So the values of MS star is given in the tables with the Mach number as I have mentioned for a particular fluid, that is for gamma is equal to 1.4. We have to remember that we have to understand that the parameter MS star and MA, in which way they are different, that we have to understand. Okay. So that just I have mentioned. MA star is the local fluid velocity to the local sonic velocity, and MA is the local fluid velocity to the local sonic velocity, and MS star is the local fluid velocity to the sonic velocity at the throat. Okay. So we can stop for now today. In the next class, we will discuss on convergent divergent nozzle. Okay.